Okay, so today we are going to talk about how to evaluate the entropy change of pure systems. So if we have a solid or a liquid, the entropy change S2 minus S1 can be determined by this equation. CV, C average temperature. So the specific heat that was evaluated at the average temperature between T1 and T2 times natural log T2 over T1. That's how we evaluate the entropy change. In this case, we assume that the specific heat is constant. And this temperature T should be in Kelvin. Okay? So that's how we determine S2 minus S1. If we have pure gases, so this one is for incompressible system. Such as solid, liquid. But if we have a pure system, pure gas, then there are two different ways to evaluate the change in the entropies. So if we have a pure gases, the entropy change S2 minus S1 can be determined by two different ways. One, assuming that specific heats are constant. So if we assume that Cp and Cv are constant, then it is Cv natural log T2 over T1 plus gas constant are natural log V2 over V1. That is one way. The other one is Cp natural log T2 over T1 minus R natural log P2 over P1. So if you know the volumetric changes, then you can use the first equation. If you know the pressure changes, then you can use the second equation. That's when we assume specific heats are constant. If we use a variable specific heat, Cp and Cv are not constant, then the energy balance equation, the entropy change can be determined by this equation. S2 minus S1 is S degree 2 minus S degree 1 minus R natural log P2 over P1. And these can be found from a property table. So from a table. Okay? So these are how we evaluate the change in entropies. So these are the things that you need to write them down on your formula sheet so you can use them in an exam. And if we can assume a reversible process, which is an isentropic process, which means entropies do not change. S1 is the same as S2. If this is the case, we can find temperature volume relations for gas. So T2 over T1 is V1 over V2 kappa minus 1. In this case, this kappa is Cp over Cv. And there's one more relation between Cp and Cv. Gas constant R is Cp minus Cv. Okay, these are just for your references. And the other one is T2 over T1 is T2 over P1 kappa minus 1 over kappa. And the last one is P2 over P1 is V1 over V2 kappa. So these are when we assumed specific Cp and Cvs are constant. If we cannot assume that they are constant, if Cp and Cv are not constant, then two equations that we can use using a table, which is P2 over P1 is PR2 over PR1, and V2 over V1 is VR2 over VR1. We can find these values from a table. So we can use these two equations if we cannot assume constant specific heats. We can use these relations for constant specific heats when we have isentropic process. Okay? So these are equations that we can use when we have a pure system. Yeah. This SDV, yeah, that you can find from a table. Yes. This one? This one? This kappa. It is Cp over Cv. That you can also find from a table. This one R. Cp is a specific heat at constant pressure. Cv is specific heat at constant volume. You can find these values from a table. We have a practice problem later, so you can see how we can evaluate them. This R is gas constant that you remember from the ideal gas equation that we reviewed. Yes. It's not K, it's a kappa. It's a Greek letter. Oh, this one? It's a kappa minus 1 over kappa. It is on the lecture note you can download from the Blackboard. Okay. Then let's solve this problem together. to use the equations that we just reviewed. By the way, these equations are what we studied in chapter 6, EGR456. Okay, this is not new. This is a prerequisite. We are just reviewing them for your information. So let's look at this problem. We have a piston cylinder device. Initially contains 300 liters of air at 120 kilopascal and 17 degrees Celsius. So we have an insulated piston cylinder device. Insulated means there is no heat transfer Q, so we neglect Q. That is insulated piston cylinder device. Contains 300 liters of air. So that is the initial volume, V1 is 300 liters. By the way, 1 cubic meter is 1,000 liters. So this is 0.3 cubic meters. Just for your information, 1 cubic meters is 1,000 liters. Okay. And we have the pressure value. The initial pressure P1 is 120 kilopascal. And the initial temperature T1 is 17 degrees Celsius. And now there is a heating process. So this heating process is different from the, the heat transfer, across this boundary. Could be electric heaters embedded inside the cylinder. So that is turned on for 15 minutes and it has a rating of 200 watts. So 200 watts. So let's say this is, so that's an electric heater. You can say Q in or W in. I'm going to say W in, not to be confused with this insulation. So W in is going to be 200 watt. And it's going to be for 15 minutes. And we assume that the pressure of air is maintained constant. T2 is the same as P1. So that is 120 kilopascal. And we want to determine the entropy change of air, assuming constant specific heats and variable specific heats. First of all, there is some mistake here that I made here. When we say W in, that is energy transfer by work. So what is the unit of this W in? Watt or Joule? Should be Joule, because this is the energy transfer, not the rate of energy transfer. So that is not power, okay? Yeah. Yeah, the unit of energy, okay? So 200 watts is Joule per second. So this one is 200 Joule per second. So if you want to determine the energy transfer by work, you need to multiply this by time t. So this one multiplied by delta t, that will give you the energy transfer by work. Then what is 200 watt, by the way? This is the power. So power can be determined by W divided by time delta t, which is W dot, okay? So when you see a dot on top of it, that means that this W per unit time. On the other hand, this W is the energy transfer by work. So this one is energy or work. This one is power. So the main difference is that, that this one divided by time is W dot, which is power, okay? And let's determine the energy entropy change of air. So how can we determine the entropy change of the air? It's going to be the final entropy S2 minus the initial entropy S1. That's how we determine entropy change. Then let's assume that this is a constant specific heat. So Cp and Cv, they are constant. Then the entropy change can be determined by mass times S2 minus S1, and this is air, so we can use this equation, either this one or this one. Since we know the pressure is constant, we can use this second equation rather than the first one because we have no idea about V1 and V2. So let's use this equation. Then this is mass times Cv natural log T2 over T1 minus R natural log P2 over P1. So that's how we can determine the entropy change. Then do we know the mass? We do not. So let's determine the mass of the system. So how can we determine the mass of the system? We know pressure, temperature, and volume. If you know pressure and temperature, you can evaluate its specific volume by using ideal gas equation. So from these two, the ideal gas equation is PV is RT, or you can say PV, the actual volume is nRT. So if we use this equation, pressure P is 120 kilopascal, which is right here, and the volume is 0.3 cubic meters. So this volume is 0.3 cubic meters, and the mass is unknown, the unknown, and R is gas constant. For air, it is 0.287 kilojoule per kilogram Kelvin, and the temperature is 17 degrees Celsius. However, if you use this ideal gas equation, the temperature should be in Kelvin. So it's not 17 degrees Celsius, you have to say 290 Kelvin. So this one is 290 Kelvin. And from this, you can determine the mass. So from this ideal gas equation, we can determine the mass, that is 0.4325 kilograms. So we can use this ideal gas equation to determine the mass of the system that goes in here in this entropy equation. So this mass is 0.4325 kilograms. And this, let's look at the second term on the right hand side. We have a natural log T2 over P1, and we know pressure is constant. So P2 over P1 is 1. So what is natural log of 1? 0. So you can neglect the second term here. So we just need to know, oh, my mistake, this is Cp. We just need to know Cp and T2, T1. We know T1, that is 290. But we have no idea about T2. So we need to determine T2 before we solve this problem. By the way, T1 is 290 Kelvin. By the way, in this entropy equation, you don't use Celsius. You have to use Kelvin, okay? Then let's determine T2. How can you determine the final temperature of the system? Other than this entropy balance, entropy equation, we can use energy balance equation. So what is the energy balance equation? Q in plus W in minus Q out minus W out is mass times U2 minus U1 plus moving boundary work WB. That is the general energy balance equation for a closed system. If you have a constant volume process, the right-hand side can be written as mass times U2 minus U1 when you have constant volume process, or you can use mass times H2 minus H1 if you have a constant pressure process. And we know it is a constant pressure process. P1 is the same as P2. So we can use this one. Then how can we determine H2 minus H1? We can use specific heat. Just for your information, specific heat equations are H2 minus H1 is Cp T2 minus T1. U2 minus U1 is Cv T2 minus T1. Of course, we got these equations from chapter 3, Thermodynamics 1. So here, H2 minus H1 can be determined by Cp T2 minus T1. And in this equation, we don't have Q in, Q out, W out. We have W in, which is 200 watt times delta T. So this equation becomes 200 watt times delta T is this one, mass times H2 minus H1. That is, by the way, Cp T2 minus T1. So we can say Cp T2 minus T1. Then delta T is 15 minutes. So that is 15 minutes times 60 seconds is 1 minute. And the mass is here 0.4325 kilograms. T1 is 290 Kelvin. And Cp can be found from table A20 here. So this one is Cp is from table A20. Then we can determine the temperature at the final state. The temperature at the final state is 698 Kelvin. So this temperature goes back to this equation. T2 here is 698 Kelvin. And this Cp is again from table A20. So we have everything we can determine S2 minus S1, which is 0.387 kilojoule per Kelvin. That's how we determine the entropy change of this air inside the piston cylinder device. Any question? So we use this entropy equation to determine entropy change. However, there were two unknowns. One is the mass of the system. The other one was the final temperature. To determine the mass, we use this ideal gas equation. To determine the final temperature, we use this energy balance equation, okay? Then let's go to the second part of the equation. The first part is when we assume constant specific heat. The other one is when we assume variable specific heat. So Cp and Cvs are not constant. Then the energy balance equation is this one here. So if we cannot assume constant specific heats, this is the equation. S2 minus S1 is S degree 2 minus S degree 1 minus R natural log T2 over P1. So let me write this equation here. S2 minus S1 is mass times S2 minus S1, which is mass times S degree 2 minus S degree 1 minus gas constant R natural log P2 over P1. In this equation, we already determined the mass of the system by using this ideal gas equation of a state. So we can use this mass in this entropy equation. So this mass M is 0.4325 kilograms. And we already know we have a constant pressure process. So natural log P2 over P1 is going to be 0. So you can neglect this one. So we just need to evaluate S degree 2 and S degree 1. To determine S degree, we can go to table A22. Here is the table A22. So then how can we use this table? We can find the specific enthalpy H, specific internal energy U, and S degree at the given temperature. So if you know the temperature, you can evaluate these three of air. So what is the initial temperature? 290 is T1. So let's find 290 is right here. So S degree at 290 Kelvin, S degree at 290 Kelvin is going to be this value, 1.66802. The unit is kilojoule per kilogram Kelvin. Unit is here. So S degree 1 is 1.66802 kilojoule per kilogram Kelvin. What about S degree 2? The temperature at the final state is 698. So let's find 698. 698 is between 690 and 700. So we have to do a linear interpolation between these two numbers to evaluate S degree between these two numbers. So between 690 and 700, we are going to do a linear interpolation between these two numbers to determine S degree at 698. If you do, S degree 2 is going to be 2.5628. 2.5628. Then this value goes in here. S degree 2 is 2.5628 kilojoule per kilogram Kelvin. So if you solve this equation, you get S2 minus S1, that is 0.387 kilojoule per Kelvin. So we get the same answer. if we use this variable specific heat method. Okay, so that's how we determine the change of a pure system by two different ways. One is constant specific heat, and the other one variable specific heat. Okay, so this one is constant specific heat, variable specific heat. You will get similar answer. Okay. Any question about this problem? So that's everything about the how to evaluate entropy. The last part of the problem is going to be entropy balance. So let's talk about entropy balance. The energy balance equation that we used is based on conservation of energy principle. So which means that energy transfer in minus energy transfer out is going to be the change of energy of the system. That's how we made this energy balance equation. So this entropy energy transfer in can be either E transfer Q in and energy transfer by work W in, and this E out, energy transfer out, can be Q out and W out, and the change of energy of a system can be E2 minus E1. That's how we made this energy balance equation based on conservation of energy principle. What about the entropy balance equation? Can we use the same conservation of entropy principle? We can't, because entropy is not conserved. On the other hand, the entropy always increases if there is a irreversibility. So we cannot say entropy. We cannot say the conservation of entropy principle. So there is no S in minus S out is delta S of the system. So this is not going to be the change of entropy of a system, because entropy should increase unless the process is reversible. However, most engineering processes are irreversible, so entropy always increases practically. So we cannot use this entropy balance equation. But one thing we know is entropy always increases. Then what about if we take this entropy increase in this equation, then we can make entropy balance equation. So we know S in minus S out is the change of entropy of a system, because if there is a process, entropy should increase. Then what about if we include another term, if we add another term, for the increase of entropy generation. So this is the added entropy when there is an irreversibility. So this is the increase of entropy when there is a process. If we include that, then we can write this entropy balance equation. So when there is a process, then we can use this entropy balance equation to determine how much entropy is generated. Okay? Then, when we have this energy balance equation, we use Q and W for energy transfer. Then the question is, how can we determine entropy transfer? So find the entropy transfer is not very difficult. There is a one rule, which is entropy transfer by heat. So entropy transfer can be either by heat or by work. And the rule is simple. Entropy transfer by heat can be determined by Q over temperature. That is entropy transfer by heat. So entropy transfer, let's say S in by Q in is going to be Q in over temperature. Then what about entropy transfer by work, W in? Entropy transfer that goes into a system due to energy transfer in W in is going to be 0. So when there is an entropy transfer by heat, we use Q in over temperature. When there is an entropy transfer for energy transfer by work, it's going to be 0. So that's how we make entropy balance equation. Okay. Then based on that, let's write entropy balance equation for a closed system and entropy balance equation for an open system. But when we study open system, many, the most open systems are steady state. So I'm going to say steady open system. Then let's talk about, the closed system first. Closed systems may have energy transfer by heat or energy transfer by work. So we are going to use either this one or 0. So the only entropy transfer is going to be Q over temperature. So when we have a closed system, it's going to be Q over temperature. How many Qs? We may have Q in and Q out. So it's going to be Q in minus Q out. There is no entropy transfer by work, so we can neglect W in, W out when we write entropy balance equation for a closed system. Then, if you have a Q in and Q out, you can combine these two. So let's say Q net is going to be Q in minus Q out. Then this entropy balance equation becomes Q over T is the change of entropy over system. Then how can we determine the change of entropy over system? Mass times S2 minus S1. So here we have an entropy generation, so this one plus entropy generation S gen is going to be N S2 minus S1. So this is entropy balance equation for a closed system. So this one here. Then what about in an open system? In an open system, we use if we have a steady open system, we know it is convenient to use a rate form. Then what is the general energy balance equation for a steady open system? It's going to be Q dot in plus W dot in plus M dot at the inlet. This one has enthalpy, kinetic energy, and potential energy. Is going to be Q dot out plus W dot out plus m dot at the exit. This one has enthalpy, kinetic energy, and potential energy. So this is the general energy balance equation for a steady open system. Then, how can we determine entropy balance equation from here? So first, for this Q, we know entropy transfer by heat Q can be Q over temperature. So for this one, we can use Q over temperature. Q in over temperature. However, we have a dot on top of it, so I'm going to add a dot on top of it here. What about entropy transfer by work? We know there is no entropy transfer by work. Look at this one. So entropy transfer due to work is going to be 0. So there's nothing here. Plus, what about entropy transfer by mass? Then it's going to be mass times specific entropy. So here we have m dot at the inlet times specific entropy at the inlet. That's it for entropy transfer that goes into a system. It's going to be the same as Q dot out. Q dot out per temperature due to this one. And there's no entropy transfer due to work. And we only have entropy transfer by mass at the exit. That can be determined by m dot at the exit times specific entropy at the exit. So this is entropy balance equation. And again, we can move this one to the left-hand side and combine with Q dot in, the same as here. Then this equation becomes, and we can also move this one to the right-hand side. Then this entropy balance equation becomes Q dot, which is the net heat transfer rate divided by temperature, is going to be m dot at the exit times specific entropy at the exit minus m dot at the inlet, the specific entropy at the inlet. So this is the entropy balance equation for a steady open system. So when you have a closed system, this is how, oh, I forgot about entropy generation. My bad. So our assumption is that there is an entropy generation, so we can add S gen per unit time. So there is S gen per unit time in front. Okay. So whenever you have a closed system, this is the entropy balance equation we can use. If it is a steady open system, this is the one. Okay. Okay. So these are the equations, these two equations, and I have a problem we are going to solve together to learn how to use this entropy balance equation. We have a steam expands in a turbine steadily. So we have a turbine. So steam expands in a turbine, that means we have an open system because this turbine has an inlet and an exit. So we have an open system. So between these two, which equation we are going to use? This one is for a closed system. So we are going to use this equation. Okay. And then let me write this equation here. So the governing equation is S dot gen plus Q dot heat transfer rate per temperature is m dot at the exit, and it's a specific entropy S out minus m dot at the inlet and the specific entropy at the inlet. So this is the governing entropy balance equation. We have steam expands in a turbine steadily at a rate of 40,000 kilograms per hour. So we have one inlet and living at 40 kilopascal as a saturated vapor. We have one exit. If we have one inlet and one exit, the mass flow rate, m dot at the inlet, should be the same as m dot at the exit. So I'm going to say, since m dot at the inlet is the same as m dot at the exit, we can just say m dot because they are the same numbers. So I'm going to remove these subscripts. And this m dot is 40,000 kilograms per hour. And we have the inlet condition entering at 8 megapascal and 500 degrees Celsius. So at the inlet, we have 8 megapascal and 500 degrees Celsius. What about at the exit? 40 kilopascal and saturated vapor. At the exit, 40 kilopascal and saturated vapor, phase change process number 4, saturated vapor. If the power generated by the turbine is 8.2 megawatt, we want to determine the rate of entropy generation, which is this one. S gen is the entropy generation. S dot gen is the rate of entropy generation. Assume the surrounding medium is at 25 degrees Celsius. Okay, so we want to determine this one, right? So let's see if we can use this equation. We already know m dot. What about S in? That is the specific entropy at the inlet. We have a pressure and temperature, so we can evaluate entropy, no problem. So how can you do that? We need to determine the phase change process. How can we determine the phase change process? By using a property diagram. So I'm going to use a property diagram here. At 8 megapascal, TS diagram looks like this. And to complete this TS diagram, we need to know T set, SF, SG. So where can we find T set, SF, SG? At 8 megapascal. So where is 8 megapascal? You see this 80 here. The unit is bar. 1 bar is 100 kilopascal. In other words, 1 bar is 0.1 megapascal. So 8 megapascal is 80 bar. So T set is 295.1. So T set is 295.1. By the way, on this TS diagram, this one is compressed liquid, saturated liquid, so this one is number 1, saturated liquid number 2, saturated mixture number 3, saturated vapor number 4, superheated vapor number 5. So, what is the temperature of the system? 500. This 500 degrees Celsius is greater than T set. So 500 should be up here. So the only phase change process possible at this temperature is going to be number 5, superheat vapor, right? So at 500 degrees Celsius, we have superheat vapor. So if you know you have a superheat vapor, how can you evaluate its property as in? You can go to superheat vapor table. Here is a superheat vapor table. At 8 megapascal, we have 480 degrees Celsius and 500 degrees Celsius. We want to determine this specific entropy S. And since we don't have 500, we need to do a linear interpolation between these two numbers to evaluate S at 500. So if you do a linear interpolation, you can determine this specific entropy. If you do, the specific entropy is 6.723. So if you get this number, 6.723 kilojoule per kilogram Kelvin. Then this number goes in here. So this one is 6.723 kilojoule per kilogram Kelvin. This value is from table A4. We already know n dot here. This one, they are the same. What about S out? We know the pressure and it is saturated vapor. So how can you determine the specific entropy of saturated vapor? The properties of saturated vapor S2 is going to be Sg. This G represents saturated vapor. If it is saturated liquid, Sf. So Sg at 40 kilopascal. At 40 kilopascal. Do we know this value? Yes, we do. We have a 0.4 bar, which is 40 kilopascal. Sg is here 7.67. So this number is 7.67 kilojoule per kilogram Kelvin. This is from table A3. That goes in here. So S out is 7.67 kilojoule per kilogram Kelvin. This m dot is again this number, right? What about the temperature? Assume the surrounding medium at 25 degrees Celsius. So this temperature T is going to be 25 degrees Celsius. Am I right? No, you have to use Kelvin. So it's not 25, it's going to be 298 Kelvin. Then how many unknowns in this equation? We don't know S dot gen, that is the rate of entropy generation that we want to determine, and we do not know the rate of heat transfer. So you cannot solve this equation because you have one equation, two unknowns. So we need to come up with another governing equation to determine this Q dot. Other than this entropy balance equation, what equation do we use? In general, energy balance equation. So we are going to use energy balance equation to determine this Q dot. So let's do that. So the energy balance equation for a steady open system is Q dot in plus W dot in plus M dot at the inlet. This one has enthalpy H in plus kinetic energy and potential energy is going to be Q dot out plus W dot out plus M dot at the exit. This one has specific enthalpy, specific kinetic energy, and specific potential energy. So first of all, you know that we can neglect kinetic energy change and potential energy change, and this is a turbine. When you have a turbine, is there W in? No, turbine is a device to produce work. So we have W dot out. We don't have W dot in. We have this one. We already know M dot is 40,000 kilogram per hour. There's no difference between M dot at the inlet, M dot at the exit, because we only have one inlet, one exit, and according to the conservation of mass principle, there's no difference. So I can remove these subscripts because they are the same. So we know M dot. The turbine, is there heat transfer? Of course, there should be heat loss from the turbine unless the turbine is adiabatic. In other words, insulated. There's no information about insulation, so we can expect that there is a Q out and there's no Q in. We don't heat turbine. So from here, you can determine Q dot that will be used to complete this entropy balance equation. Okay? So let's see. We already know M dot. M dot is 40,000 kilogram per hour. By the way, this is per hour. You want to, to correct this one, multiply by 1 hour over 3,600 seconds because we prefer kilogram per second, right? What about H in? We already know at the inlet we have a superheat vapor, so you can go to superheat vapor table to determine H in. There is superheat vapor table, table A4, and here we use the linear interpolation, so we are going to do that again for this H. So this time we are going to determine H in. Where is H in? Between these two numbers, there is a H in. You can do a linear interpolation to determine H in. If you do, H in is 3398.05. So if you do this one, it is 3398.05 kilojoule per kilogram. This value is from table A4. Q dot out is the unknown. W dot out. Do we have W dot out? According to this problem statement, it says the power generated by the turbine is 8.2 megawatt. So this is the W dot out. 8.2, 8,200 kilowatt. We know M dot, 40,000 kilogram per hour. What about H out? At the exit, we know it is 40 kilopascal and it is phase change process number 4. So H2 can be determined by Hg at 40 kilopascal. So from here, H2 is Hg at 40 kilopascal. So do we know this number? Yes. At 40 kilopascal, Hg is here 2636.8. So at 40 kilopascal, Hg is here, this number, 2636.8 kilojoule per kilogram. This is from table A3. So this one is 2636.8 kilojoule per kilogram. So we have everything but Q dot out. So can you determine Q dot out? Yes, if you do, Q dot out is going to be 258.33 kilowatt. So this is the rate of heat transfer from the turbine to the surroundings. So now this number goes back to this entropy balance equation. Here, Q dot, so I'm going to substitute this number, 258.33, 258.33 kilowatt. Then you get S dot gen. Am I right or there's a mistake? There's a mistake, which is this one is Q dot out, the rate of heat transfer from the system to the surroundings. This Q dot is the net heat transfer rate. So we need to add a negative sign to show that this is outgoing heat transfer rate. So this one is minus 258.33. Then we have everything but S dot gen. So if we do the calculation, it's going to be 11.4 kilowatt per Kelvin. Okay, that's how you solve this problem. Any question? This completes the review for EGR456. You have a new homework assignment, which is due a week from today. So it's going to be 12:30 p.m. next Tuesday. Okay. Any question about Thermodynamics 1 before we start Thermodynamics 2? Yeah. You have 12 minutes. So that's plenty of time. You can finish a lot of them, right? Thermo 2. You're supposed to be very happy because we are now starting Thermodynamics 2. In the past, the few days we were, the reviewing those that we already know. I'm pretty sure that you got, the really bored, right? So some of our analysis in Thermodynamics 2 is on molar basis, which is different from mass basis. Everything that we studied in Thermo 1 is on a mass basis. So when we talk about specific internal energy, it is kilojoule per kilogram, right? But on a molar basis, it's going to be kilojoule per kilomole. So we need to first understand how to convert between mass basis and molar basis. Okay. So we are going to study, how to, deal with problems on a molar basis. So to do so, we need to understand, how to convert between mass and a mole. So the main equation that we are going to use a number of times is going to be this one. N is N over M. There are too many M's, right? So this N is the number of mole. Lowercase m is the mass of the system. This capital M is molecular weight. So if you want to determine how many moles in the system, we can use this equation. So N is N over M. N is M over N. M over M, like, like a M&M, right? So then where can we find this capital M? It is molecular weight. Molecular weight. The molecular weight. Where do we find this molecular weight? From table A1. So let's go to table A1. If you go to table A1, you see this capital M. This is molecular weight. Look at the unit. Kilogram per kilomole. Kilogram per kilomole. So that means this is the weight. This is the mass of the system when you have 1 kilomole of your system. And let's look at the one of the common units, common the gases. Look at this one, oxygen. Oxygen. The molecular weight is 32 kilogram per kilomole. So the molecular weight of oxygen is 32 kilograms. Molecular weight of oxygen, O2, is 32 kilograms per kilomole. Then if I, ask, how many, how many moles of oxygen if you have 64 kilograms of oxygen. And it's simple. You have a 60 m over molecular weight of oxygen. So the mass of this oxygen is 64 kilograms, and the molecular weight from table A1 is going to be 32 kilogram per kilomole. So this one is from table A1. So the number of moles in the system is going to be 2 kilomoles. Very simple, right? Then we are going to study fractions. The first one is mass fraction. The other one is mole fraction. The mass fraction means when you have a mixture, because the most materials that we are going to study are mixtures, like the moist air. If you have a moist air, what do you have? You have air, which is oxygen, nitrogen, carbon dioxide, etc., 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 and there is a water, H2O. So when we talk about moist air, which is the actual air, rather than the dry air that we used in EGR456. So most of the gases, that we study are mixtures. So we need to know how they are mixed. So that is mass fraction. So mass fraction means mass fraction can be determined by this equation. MF, mass fraction, of component I can be determined by mass of that component divided by M. Then, when you see this one, I know what is M, that is mass. And what is MI? Michigan? No. It is mass of I component. So, for example, let's talk about air. Always easier to understand, if you use an example. Air can be considered as a mixture of oxygen and nitrogen. Of course, you can say carbon dioxide, and sulfur oxide, and et cetera, but the majority of air is going to be 79% of nitrogen and 21% of oxygen. Then, how do we determine the mass fraction? To use this equation for air, we can use it in this way. Mass fraction of oxygen, O2, is going to be the mass of oxygen over M. When you see there's no subscript, that means this is the total mass. So let's say when you have air and oxygen is 1 kilograms and nitrogen is 4 kilograms, then the total is going to be 5 kilograms. Then what is the mass fraction of oxygen in this mixture? Then the answer is the mass of oxygen is 1 kilogram and the mass of the total is going to be 5 kilograms. So the mass fraction is going to be 0.2, in other words, 20%. That's how you determine the mass fraction. Then how many mass fractions do we have for this system, air? Since air is considered a mixture of these two, oxygen and nitrogen, there are only two mass fractions. Mass fractions of oxygen and mass fractions of nitrogen, which is mass of nitrogen divided by mass. In other words, 1 at 4 kilograms divided by the total mass 5 kilograms, 0.8, so 80%. So when we combine, when we calculate the sum of all the mass fractions in a mixture, that's gonna be 1. So mass fraction of oxygen plus mass fraction of nitrogen should be what? 1. 100%. And you may think that, oh, this is too easy. I thought that, the Thermodynamics2 is quite challenging. Then this is not what I expected. Then you can talk about mole fraction. Then what is mole fraction? Mole fraction is the fraction when you consider this mixture on a molar basis. So how can you determine the mole fraction of this mixture? By the way, mole fraction means mole fraction is Y, mass is M, number of mole is N. So we use mass on a mass system, we use N on a mole system. Then what is mole fraction? Instead of NF, we use Y. So Y of oxygen is going to be the number of moles of oxygen divided by the total number of moles. And similarly, we can calculate the mole fraction of nitrogen, which is the number of moles of nitrogen divided by total number of moles. Then, if we have a mixture of 1 kilogram of oxygen and 4 kilograms of nitrogen, what is the mole fraction of oxygen? So we can ask that question, right? So let's see. If you want to determine the mole fraction of this system, 1 kilograms of oxygen and 4 kilograms of nitrogen, you first need to know how to convert between mass and the number of moles. How do we do that? By using this equation. N is what? M over M. If you cannot remember this equation, N is M in M. Easier, no? Okay. Didn't work. So N is M over M. So if you want to determine the mole fraction of oxygen, you need to determine the number of moles of oxygen first. So let's do that. NO2 is going to be NO2 over molecular weight of oxygen. So what is the mass of oxygen? 1 kilogram. So I'm going to say, okay, this one is 1 kilograms. What is the molecular weight? If you want to determine the molecular weight, you can go to table A1, which is here, 32 kilograms. 32 kilograms per kilomole. Then you get the number of moles of oxygen. You can do the same for nitrogen. And is M over M. So we can determine the number of moles of nitrogen, the mass of nitrogen, the molecular weight of nitrogen. In this case, this one is 4 kilograms. What is the molecular weight of nitrogen? The molecular weight of nitrogen is 28.01 kilogram per kilomole. So you can determine the number of moles. Then once you determine these two, then we can calculate the molar fraction of oxygen, the molar fraction of nitrogen. Since we are running out of time, we will calculate this molar fraction of oxygen and nitrogen later this Thursday. Actually, you can do that by yourself because you have all the values to calculate the number of moles of oxygen and nitrogen. Okay? That's all. Thank you.